Okay, well, thank you very much for all being here. Thank you to Barbara for inviting me, and I understand Patrick as well for providing some of the money too. So that's great. So please do interrupt if you feel inclined to. So I'm going to talk about, well, basically this big question that is outstanding right now. What are the LLSVPs or LLVPs? I just wanted to start off by pointing out that all the models, as we've just seen, that tomographically image the inside of the mantle, pretty much agree, and they also pretty much agree with some of the very first models. So, I mean, the Earth in 1984 doesn't look so different to how it does today, in fact. We still have these two broad regions of low velocities, and even the shape of the LSVPs are really well recreated by these early P-wave models. So the question then arises, what are they? And at the time, a lot of people called them super plumes. They were thought maybe to be big, large, homogeneous upwellings. But things have sort of changed. And I also wanted just to show in cross-section Jeroen Ritzimer's model, and even in these views, we see these sort of sloping structures and things like that. Things that, again, don't necessarily look like a classical plume, which would always want to rise vertically. So the LSVPs take up a pretty large volume of the mantle. And the question is, are they involved with convection? So are they sort of moving in response to thermal effects only, or do they influence the convection because they're chemically different? And if they are chemically different, that's quite appealing, because we need hidden reservoirs of things like noble gas isotopes, things like helium-3, to come from somewhere, because we know they exist somewhere hidden in the mantle. So it's very appealing to think that these LLSVPs are big piles of different material which haven't been involved with convection all the way throughout the mantle. So some of the more recent lines of evidence towards one or the other have sort of been muddied recently. Now, obviously, if you could just directly measure the density of these things, you would have quite a good answer to that sort of question, whether they're dense piles or sort of thermal plumes. And the early inversions of normal mode data for the density structure of the mantle seem to provide pretty good evidence. So dense regions here are in blue, and the higher up in the mantle we don't see the same pattern, but at the base we pretty much mirror the tomography and have dense regions where the large low velocity provinces are. But more recent inversions using modes which are sensitive to structure nearer the core mantle boundary seem to disagree with this. So this isn't such the closed case that it was considered to be for a long time. Other really good evidence for whether the LLSVPs could have a large chemical component to their different velocity come from looking at the bulk versus the shear wave versus the P wave velocities. So the bulk velocity isn't associated with a wave we physically observe, but it's a measure of the bulk modulus, the material, in the same way that the shear velocity is a measure of the shear modulus. And this can be obtained by combining the P and S wave velocities. Now you need to do that carefully because the sensitivity of those two measurements wants to be the same. But when Guy Masters did it, and others as well, what we see is a map here at the base of the mantle, and in these LLSVPs, there seems, certainly at least beneath the Pacific, to be a strong anti-correlation between the two. Now, if you think about the construction of these velocities, it's very difficult to imagine a way of going with purely temperature to make something slower in one but quicker in the other, because you'd have to modify these moduli in different directions. So that was interpreted as very strong evidence for a chemical difference. But 2004, the discovery of a new phase potentially that existed at the base of the mantle post-perovskite, a structure beyond the perovskite structure of Bridgmanite. This effect is it turns out that the elastic properties of these minerals exactly would give you this bulk sound, shear sound anticorrelation. So we have an alternative explanation now. And also, if indeed these regions in the Pacific underneath Africa are hot, then this is exactly the pattern we would see mineralogically. So it's stuck in the air. Okay, so that one's a big question mark too. And there are other lines of evidence where the waters are muddied somewhat. The more you look at it, the more complicated it gets. It's what always happens. So some of the observations that we've relied on most recently to say that these are chemical features and they're sort of intrinsically dense, say, has come from looking at gradients in the velocities. Now, the argument is that you can only sustain very sharp gradients in velocity laterally, not thermally, because that should diffuse away, but with a chemical difference. Now, this map here is a sort of a compilation of tomographic images, and each point on it is showing the range between the fastest and the slowest shear wave velocities within a certain radius. So this is within 5 degrees of each point. What's the range of velocities you experience? And you see that around where the slow regions are, you have a large range of velocities. And so that's sort of a measure of how sharp the edges of these features are. So that's some evidence just using tomographic models. We also have lots of direct observations when we study the waves in great detail, looking at the waveforms. So this is some data that we've seen before, in fact, today. So Sonna just presented this. So when we have earthquakes that are over the southwest Pacific, and we measure them at the Kapval array in southern Africa, we observe this. So get your seismologist eye in. If you're not a seismologist, we'll have some practice at this today. So what I'm showing here is the arrival time relative to the predicted arrival time of an S-diff wave if the mantle was just radially symmetric. And you see that as you go up in azimuth, so basically as you go from south to north at these stations, the waves arrive later and later and later until we get to some point where there's a jump. And at this jump, there's a kind of complication in the waveform. Now, you heard Sana mention this. This is what's called multipathing in this region here. And then after this jump, things arrive even slower. And this was interpreted simply by saying there's a sharp jump between outside this African anomaly and inside it. And at the edge of it, we experience this sort of multipathing effect. So this is the way Al Hoffman explained multipathing to me, which I thought was excellent for someone that does what he does. So it's a simple concept. What happens is that when we have a wave that's propagated away from an earthquake somewhere over here, Fermat's principle applies. What that says is the first arriving wave may not have taken the most direct route, but it will have gone through the material with a higher velocity, providing you're not too far off the path. So your first arrival actually travels just around the edge of the LLSVP. It's refracted round, and slightly later, or in the same arrival, something which has experienced more of the slow material also arrives. And so we have two arrivals. It's multipathing, but you're only going to get that where there's a really strong lateral gradient in velocities here. So this observation is potentially very powerful for letting us observe these sharp edges. But how to test whether or not this assumption that it only happens where you have chemical heterogeneity is true? Well, we're just going to use an approach of testing two possible end members here. And we have two geodynamic models where we have patterns in the mantle which are similar in the sort of length scale and where features are compared to today, but they're not meant to be exactly the same as today's mantle. Okay, these are models. So these are two classes of convection simulations. That means that we're imposing plate motions for the last 300 million years to simulate those surface velocities. And these are done at a high Rayleigh number, about 5 times 10 to the 8, to try and get the vigor as close to the Earth as we possibly can. So the top row here, these models are not new. This is the work that Rodri Davis showed a while back. These models at the top, we show here sort of the variations in temperature, the absolute temperature, for different slices And so you can see we have features such as subduction zones where we've imposed convergence and upwellings away from those plates that have fallen down to the base of the mantle. But in this model, the only thing that varies is the temperature naturally. In this second class of models, this thermochemical regime, we have large piles of intrinsically dense material. They're about 3% denser. And they tend to stay near the base of the mantle, but you do see sometimes they're entrained into plumes, but otherwise they form these large piles. And so we have a temperature field and a composition field in this case. Now, if we want to investigate these seismically, we need to convert this from the temperature, pressure, and composition into seismic velocities. We do that using Hephaestus inside our conversion, and we go from this temperature field, for example, here, to this velocity field. And so you can see these sort of features that we might expect to exist in the mantle. As you point out, we also include attenuation in all of these calculations as well. It doesn't make a difference really in the end to what we're observing here, but this is just treated as another parameter that comes out of the our Hephaestus calculation. So one thing that was done at the time, and it's an obvious thing to do, is to compare these with tomography. Now, tomography is a combination of the choices you make in terms of how you retrieve your velocities from your data, and also where your data is. It's difficult to do much about that in the Earth. And combining those two gets you to an image of the interior of the Earth. Now, we're starting out with perfect knowledge of what the structure is. So what we can do is use this combination of data and the inversion procedure and the damping and so on to get to what the mantle would look like tomographically for this particular model that we're looking at. Now, here's just the example. Here you see that the thermal model and the thermochemical model, once you've done this and compare it to S40 RTS in this case, they both look very, very similar, and arguably it's difficult to distinguish between the two. If anything, the thermochemical piles end up giving you regions that have very, very low velocities, possibly lower than you might actually be retrieving in the tomography. They might exist, despite the tomography damping it down. So these sharp sides then might be the discriminant that we're looking for to tell these classes of models apart, which one better represents the kind of observations we can see in the Earth. Now, the first thing to look there for is for these lateral gradients that occur. So these lateral gradients, these sharp changes from high velocity to low velocity or vice versa, are where we expect to get these multipathing effects at the edges. So here I'm just showing the lateral velocity gradient in kilometers per second per degree. So that's per about 50 kilometers or so at the base of the mantle. And what you see is that the thermal model and the thermochemical model both produce very large lateral gradients. This is an effect of the temperature and the composition. Now, these gradients are large. They're certainly large enough to produce this kind of multipathing that we observe in seismograms. And even the pattern is not so different. What you can see in the gradients actually is the sort of the planform of the plumes that are rising up here and the outline of the piles. And they both give you these strong gradients. So if we want to investigate whether or not actually the 3D structure of these things has some correspondence to reality, we need to do some waveform simulations, which is what we do. And you've just seen some of these data before. So this is an earthquake on Tonga, Fiji subduction zone, a nice deep one, measured at this cut val array. And obviously we simulate lots of seismograms. We're just going to look at this example. And we have this sort of range of azimuths that we've shown before. So let's do some seismology. One of these is the data. Two of them are the two models. Okay. Does anyone want to guess which one is the data? Left. Excellent. There we go. You see, a room full of professionals. This is great. Okay, so this is the data. So we've just seen it. This is just in velocity now rather than displacement. So the wiggles go down and up rather than only up. So there's some features to note. And I should say, because you're all thinking, the features that we're seeing here aren't affected very strongly by the anisotropy that is present in the data. That is a secondary effect on the pattern we're looking at. First thing to note is that at these small azimuths, I'm plotting azimuth against time relative to the predicted travel time here, we have sort of these large amplitudes, we have a sort of very gentle gradient in the arrival time. Then we get into a region where it's more complicated. There's sort of a change in the amplitude and there's a slope in the arrival times. And then at the highest azimuths, the amplitude goes up again and we have a more sort of normal slope in the arrival times. And the keen-eyed seismologist, such as Carolina here, will note that actually you get this secondary arrival coming in. So it is there. It's clear in the displacement, but you still see the velocity nice and easily. Okay, so that feature is your multipathing, basically. Now we can reproduce that in both of our models, in both our thermal and our thermochemical models, very easily. Now the character of it and the arrival time is slightly different, but we see it in both cases, and this really just depends on the exact geometry that you're looking at. Remember, this isn't the real Earth, even though we're simulating along the same path, which I think is remarkable. So depending on where you go, you'll see slightly different effects. Now, does anyone want to guess which one's the thermal and which one's the thermochemical model? Left or right? No one wants to put their neck on the line. It's okay. There's the answer. But you couldn't tell really obviously before you knew. So both of these models produce these classes of features that we see in the waveforms. How do we know this is multipathing? Well, we can actually track back where the energy came from. So we can use this sort of FK analysis, where what we do is we use an array of stations, which we have, and we essentially search over all possible incidence angles and azimuths of the energy coming in, stack that up and find where the power is strongest. And this is an example. This isn't our data. This is from a different array. For instance, here the dot's the sort of the theoretical arrival, and the colour shows you the stacking power. And you can see that in this case the arrival has come in at the same sort of incidence angle and back azimuth that we expect. We can do this with the data, for instance, and we see that. Well, okay, so it's quite difficult. I'm afraid the theoretical arrival is slightly lost in these plots. The arrival is coming in at a different back azimuth and slightly different slowness. So we're not going along the expected route. We're going up, skirting around the outside, and we're getting this multipathing. And we can do exactly the same thing for the synthetics. Here I've just filtered them at different frequency bands to show you that you can still discern this multipathing for the different sets of azimuths in the two different classes. So we can't tell the two types of models, thermal or thermochemical, apart this way either. And just to show you this graphically, what's happening at low azimuths is we're skirting around the edge of this sharp gradient, and then we travel through it, and this is when we start to see this multipathing, because some of your energy is arriving in a different direction than you expect it to. Okay. SDiff isn't the only phase that we can use to investigate this. So it may be that we're sort of biased by a particular way of looking at the data. So this SKS wave is very popular, and again, this is this cross-section through the African LLSVP, and we have this green outline, which is the Don Helmberger favourite structure that we might see there. It matches quite well with the tomography. This SKS wave is useful because it has a sort of fairly steep path in the mantle. And what you can do is you can search around, cross over the edges of the tomographically slow regions, and try and find where the multipathing occurs. That should give you basically a map of where these sharp sides are. So again, we can reproduce that. Now, you can tell you're a senior scientist when you don't have time to reproduce your plot properly, and instead you have to change the aspect ratio so your focal mechanism becomes an oval. So I think that means I'm getting up there in the seniority stakes. But anyway, so we can take a synthetic experiment, fire off an earthquake from up here, and what we're seeking to do is measure the edges, those sharp edges around the African anomaly. And this is just an example of the sort of synthetics where you go from arrivals that are coming in at a certain time, and once you cross over into the slower region, they arrive later, and we have this sort of edge effect happening. So what we do is we look at a lot of seismograms, we work out where the multipathing occurs, and we plot it up on a map. Okay? This is what the map, so this box here is the sort of where the stations are, this star is where the earthquake was, and if we take a plot of the gradient in the thermal model, we can see that these purple dots, which show where the multipathing is observed in these SKS waves, unsurprisingly, they occur where the steepest gradients are, and these are basically where the upwellings are occurring. And if we go higher up, so 100 kilometers above the CMB, we see actually the gradients get stronger, and so the points where we see this multipathing occur actually are higher up in the mantle. They're not right at the CMB. This is actually being caused by gradients higher up. We'll come back to that in a sec. But as you can see, it's pretty obvious where we're going to detect it, and indeed we do. Let's have a look at the thermochemical model. In the thermochemical model, we have a slightly different morphology, and we have these sharp gradients at the edges of the dense piles. Now, if we take a section just above the core mantle boundary, where these piles are located, and we plot up again in purple where the multipathing occurs, it doesn't actually happen at the edges of the piles. It happens slightly inside. Now, as we move up radially, so now we're 100 kilometers above the CMB, we're still actually not coinciding with the edge of the piles. We have to go further up into the mantle where the gradients are now moving towards where we see the multipathing occur, and they get stronger. So what is this? What's going on? And if you're a corner, you might say we're in the city of love, and that's something that comes out of these models. So the first thing to sort of presume is that if you have dense material that is at the bottom of the mantle because of that density contrast, it's always going to seek to sort of splay out, and the denser it is, the larger the aspect ratio, so it's going to be flat and not very high. So this is just an example of a convection simulation with dense material that's accumulated at the bottom, and you see the sides of the piles are always, there's always a slope to them. So you could argue that perhaps you're not sampling the edge when you're right at the edge of the pile. You're not going to sample the edge and produce multipathing in the same way. And in fact, you probably need to be looking at the right geometry. But it doesn't seem to be as simple as that. Let's look at some cross sections of these gradients in velocity in the models. So again, up above we have, so this is a cross section going across the African anomaly again. If we look at the thermal and the thermochemical models, let's take the thermochemical pile. You can see the outline of the pile here. And you do have a lateral velocity gradient, but because of the slope on the edges, it's not that strong. But even if it were vertical, it wouldn't be anything like as strong as these gradients we see here. And this is true for the thermal case as well. Now, if this is a velocity section, this is a plume. So this plume produces a very strong velocity gradient. And because our SKS wave is nearly vertical, it samples it for a very long way. And the multipathing that we observe in our synthetics and in the synthetic model is due to the plume. This is also true for the pile. The reason that our multipathing doesn't occur right at the edge is because it occurs where the stars are, it occurs where the plumes are, which happen in this model to arise in off the edges of the slabs, of the piles. So if I were to conclude here, which I will, you'll be glad to know, do these sharp edges have to be in chemical models? No, they don't. And I think we knew that, actually. I think we did really knew that, but we got hung up on it for a little while. So even in a purely thermal model, you still get these strong lateral gradients, and they do lead to multipathing, just like we observe in nature. And I think it may be that actually these sharp sides don't represent necessarily what we think they do everywhere. And if I were to be controversial, I would say maybe we've already directly detected mantle plumes, but we need to do a lot more looking. Thank you.